artificial intelligence paper that IISc has published. So we'll solve the DBMS part of it. Yeah, so we have three 1 mark questions and four 2 mark questions. Okay, so the first question is that consider two relations. The first relation is R and it has the attributes X and Y. And the second relation is S. It has the attributes X and Z. So the relation R has 100 records and the relation S has 200 records. So they're asking us what will be the number of attributes and records for the query given. This is the query given, that is select star from R cross join S. Okay, so first let's recall what cross join is. Right. So we have seen different joins. Cross join is basically equal to the Cartesian product of the relations in question. Okay. So if we say R cross join S, this is equivalent to saying R cross S. That is the Cartesian product of R and S. Okay. So now coming back to the question, uh, we are saying R cross join S. So here what we'll do is we'll perform the Cartesian product of R and S. Now, when we have the Cartesian product, uh, what is the number of tuples we have? So the number of tuples in the Cartesian product is equal to the number of tuples in R into the number of tuples in S, right? So this gives us 100 into 200. Okay. So we have 20,000 records. So based on that, we are either option A or option B. Now coming to the attributes. So when we take the Cartesian product, the Cartesian product of R and S would look something like this. It would have all the attributes from both the relations. We have X, Y, then X and Z, right? So this is how your Cartesian product looks like. So we have total of 4 attributes. So based on that, the right answer is B. Okay. So we have 4 attributes and 20,000 records. So moving on to the next question. Yeah. So we have two relations in this question again. One is the relation R, which has two attributes X and Y. And the second relation is S, which has only one attribute Y. And we have to perform the operation that is the divide operation. So we are saying RXY divide S of Y. Okay. And whatever is the output that is named as X of R dividers. So we are given some statements about uh, the cardinality of X and let's see what we can do with it. So the first thing is we want to find what the division operation is going to do. Okay. So we have R relation R that has the attributes x and y, and we have the relation S that has the attribute y. Okay, so in questions like these, when it is uncertain because we don't have the exact relation, what we can do is we can try to find counter examples to negate the statements in the question, right? So the first point that comes in division in R divide S is they should be compatible for division. So for that, the attributes in S should be a subset of the attributes in R. So that is the case because we have the Y attribute here, and that is a subset of the attributes in R. So they are division compatible. Now, the second thing is what is the division operation going to return? So R divide S in this case is going to return all the values of attribute X that match with all the values of attribute Y in R that match with all the values of attribute Y in S. Okay. So based on the definition, one thing is sure, right? That whatever we do, the cardinality of R divide S is definitely going to be less than the cardinality of less than or equal to the cardinality of R, right? Because as based on the definition, all the values of attribute X in R that match with all the values of attribute Y in S. So definitely it is going to be a subset of the relation R. So this statement is for sure. So based on that, we can say option A is right. And this is, I think, a multiple select question. So we have multiple options too. So we'll have to check if the other statements hold. Yeah. So the second statement is that the cardinality of X, that is R divided S, is less than or equal to the cardinality of S. So we'll try to come up with an counter example for this. Let's say we have 1, 2, 1, 3. Let's say we have 2 and 3. Okay. We have 1, 2, 1, 3, 2, 2, and 2, 3. Okay. So we have 4 tuples in R and we have 2 tuples in S. Right. So the definition says that the output is going to have all the values of attribute X in R that match with all the values of attribute Y in S. So we want to see all those values in this column that match with all the values of Y here. So basically all those values of X that have a matching tuple with the Y value as 2 and 3. So we have 1, it matches with 2 and 3, and 2 also matches with 2 and 3. So the output R divide S would have X, 1 and 2, right? So now in this example, the cardinality of R divide S is less than or equal to the cardinality of S. But What if we had more tuples here? What if we had 3, 2 and 3, 3? What if we had 4, 2 and 4, 3? Right? In the relation R. So in that case, our output would be extended, right? We would have 3 and 4 as well. So that gives us a cardinality of 4, which is greater than the cardinality of S. So we have come up with an example that negates this. So this one is wrong. And again, since B is false, C also has to be false. And obviously, based on the definition, the cardinality of X can never be greater than the cardinality of R, right? Because it is a subset of R. So this is wrong again. So the answer is option A. Okay. Okay. So in this question, we have to they are given statements, and we want to see which ones of these are true. Fine. So the first statement is that every relation in BCNF is also in 3NF. Okay. So we had seen this, right? This is 1NF. Then we have 2NF. Then we have 3NF. Then we have BCNF. So it was like 2NF is a subset of 1NF, 3NF is a subset of 2NF and 1NF, and BCNF is a subset of 3NF, 2NF, and 1NF. So if a relation is in 2NF, then it is also in 1NF. If a relation is in 3NF, then it is also in 2NF and 1NF. And if it is in BCNF, then it is in the all 1, 2, and 3NF. Right? So the statement A is obviously true because BCNF is basically stricter than 3NF. So every relation in BCNF is obviously also in every relation in BCNF is also in 3NF. So option A is right. And let's look at option B. Option B says that every relation with two attributes is in BCNF. So we had seen this in the classes on normalization, right? We had seen the proof for this, that every relation with two attributes is in BCNF. So if you go through that class, you can go through the proof for that, that every relation with two attributes is in BCNF. Basically, what you can do is you can take a relation with two attributes, A and B, and you can try out the different functional dependencies. So you can create the functional dependency set, right? Functional dependency set. You can have any functional dependency there, and based on that, you can see that this statement holds. For BCNF, the only thing is that the attributes on the LHS in functional dependencies should be a super key. Right? So option B is also true. Now let's look at option C. So option C says that no relation can be in both BCNF and 3NF. Right. So again, based on this figure that we are seeing, if a relation R, let's say, is in BCNF, then it is in 3NF, 2NF, and 1NF, right? So If a relation is in BCNF, it has to be in 3NF, and therefore it has to be both BCNF and 3NF. So this statement is clearly false. And if you look at option D, it says that every relation in 3NF is also in BCNF. So let's take a relation S that is in 3NF, right? Since BCNF is a subset of 3NF, it need not be the case that any relation in 3NF is also in BCNF, right? Remember that for 3NF, we had seen the rule that uh, the LHS can has to be super key in the functional dependency set, or the RHS has to be a prime attribute, right? And for BCNF, the LHS has to be super key, right? So if we look at the definition also, BCNF, 3NF allows though even functional dependencies where either of these are true, right? So this is or. So either the LHS can be a super key or the RHS can be a prime attribute, right? But BCNF is stricter. It says that the LHS has to be a super key and those are the only functional dependencies that are allowed, right? So clearly we can have a relation that is in 3NF which has the second type of functional dependency wherein the RHS is a prime attribute but the LHS is not a super key. So that will give us a relation that is in 3NF but not in BCNF. Your statement D also has to be false. Every relation in 3NF is not does not need to be in BCNF, but every relation in BCNF has to be in 3NF. Okay. Let's move on to the next question. Okay. So we are given this relation instance. We have three attributes x, y, z, and we have these tuples. And the question says we have to find out which of these following options is true, or which of the following functional dependency sets hold true. Okay. So we'll look at the options one by one. Okay. Let me first write down this. We have x, y, z. Right. We have 142, 153, 142, 153, 143, 152, and 321. Okay. Now the first option says that xy derives z. Okay. So for this functional dependency to hold, if for every unique value of xy, the value of z should also be unique, and particularly one, let's say we have a pair of xy values a b in one of the tuples the value of z let's say is a, then in another tuple we cannot have the value of z as c. So basically every value of xy should only derive one value of z and that value should be unique. So we can look at it. We have xy gives z. So we have 1 4 1 4 2. So what we have to check is of if this functional dependency does not hold 1 4, we have to check if 1 4 derives another value apart from 2 as well in the same relation instance. So we have 1 4 derives 3 here, right? So xy gives z does not hold. Okay. Now we look at in option A, the second functional dependency is z gives y. So we'll look at that. So z gives y. The first tuple has 2 derives 4. Then we have 3 derives 5 and 3 derives 4. So 3 derives two values, 5 and 4. So this functional dependency also does not hold. Now we look at option B. The first one is yz gives x. Okay. So yz gives x. So we 4 2 gives 1. Let's check if 4 2 gives another value there. So no. 5 3 gives 1. Does 5 3 give another value in the same relation? No. So we are fine here up to here. 4 3 gives 1. We are fine up to here as well. 5 2 gives 1. We're fine. And 2 1 gives 3. So we are fine. So yz gives x holds. Now we have to look at x gives y. So x gives y is clearly false because 1 derives 4, 1 derives 5. So it does not hold. Now in option C we have y derives x. So 4 derives 1. Does 4 derive anything else? 4 derives 1 here. So we are fine. 5 derives 1 and 5 derives 1 here. So we are fine. And 2 derives 3. So we are good. Y implies x. And x implies y. We have already seen it does not hold. Let's look at option D. Xz derives y. So 1 2 derives 4 and 1 2 derives 5. Right? So xz gives y does not hold. And y gives x. We have seen that it holds. Right? So I think there might be some misprint in the options here. Uh, because none of the options in this are true. So we have seen that yz gives x is true and y gives x is true. So these are the two that are true. Okay, fine. Let's move on. Okay, so we have this question from B plus trees. So this question is a little tricky. We'll try to solve it. So a file, we have a file that has 100,000 records, and we are creating an index in the form of a B plus tree, right? So the block size is 2k bytes, that is 2048 bytes, okay? And the size of the key is 4 bytes. The size of the pointer is 4 bytes, And we have to find the minimum possible height of the B plus tree index. We have to see what is the minimum height we can have in a B plus tree. And the hint they've given is no records are stored at the nodes. Okay. Only keys are stored. And the sizes of the pointers are the same, irrespective of whether they point to a node or a record. Okay. So, first, in B plus trees, we have two types of nodes, right? We have the leaf node and we have an internal node, right? So the leaf node has keys and record pointers, right? We have these pairs and so on. And we have another pointer that points to the next leaf. So this is the structure of the leaf node, and the order of a leaf node is equal to the number of key value pairs it stores. Or instead of saying key value pairs, let's say key plus record pointer pairs. Okay. The internal node has a block pointer followed by a key followed by another block pointer. Right. This block pointer points to the children. Right. Followed by another key followed by another block pointer and so on. Right. And the order for the internal node is the number of children. Okay. Okay. So this is the basis for this question. Now, so we have to find the minimum possible height of the B plus tree. So the height of the B plus tree would be minimum when all our nodes are fully filled, right? If we have the leaf nodes as fully filled, if we have internal nodes that are fully filled, so in that case, the height of the tree would be less. And if we try to keep the leaf nodes or the internal nodes empty, we'll wind up with a B plus tree that is greater in height because we have to store 100,000 records. Right? So the size depends on how much you are, how many, what, yeah, how many key and record pointer pairs you're storing in the leaf and how many keys you're storing in the internal nodes. Okay. So what we have to try to do is we have to try to maximize the number of key record pointer pairs that are being stored in the leaf node and also try to maximize the block pointers in the internal nodes. So these are the two goals that we have if we want to minimize the height. Fine. And since every node is stored in one block, so one node can span maximum of 2048 bytes. Okay. Now, uh, let's say that order of the leaf is PL. Okay. So if the order of the leaf is PL, we have PL key and record pointer pairs. So how much space will that take? The key takes 4 bytes. Then we have another 4 bytes for the record pointer. And this is PL. And we have another block pointer that points to the next leaf. So that again takes up 4 bytes. Right? So that gives you 8PL plus 4. Okay. 8PL plus 4. Now, if we want to maximize PL, we have to see that basically 8PL plus 4 should be equal to 2048 bytes, right? That is when PL will be maximum if you're utilizing the entire node size. Okay. So that gives us PL is equal to 2044 by 8, which is I think 255.5, right? Okay. So basically it's saying that the order of the leaf should be 255.5, but obviously we cannot store 255.5. So what we'll do is we'll store 255. Okay. Now let's do the same thing for the internal node. Okay. So let's say that the order of internal node is Pi. Okay. So that means we have Pi each internal node can have a maximum of Pi children. So we have Pi block pointers. Each block pointer is 4 bytes. So 4 Pi, right? And we have Pi minus 1 keys, which are also of 4 byte size. So that is equal to 8 Pi minus 4. And 8 Pi minus 4 should be equal to 2048 for maximum uh, size utilization. So that gives us Pi is equal to 2052 by 8, which is I think 256.5. So we'll take that as 256. Okay. We have the maximum order of the leaf as 255 and the maximum order of the uh, internal node as 256. Okay. Now, sorry. Yeah. Now we'll calculate the number of leaves. So the number of leaves will be equal to basically 100,000 records are there. So your leaves will point to 100,000 records and we'll divide that by the order. How much can we fit in one node? So that will give us the total number of leaves, right? So this comes out to be I think it will be 392 point something, right? So point something means we'll have to add one more leaf node. So we have 393. 393 leaves. Okay. So now since we have 393 leaves, our internal nodes should point to all of these 393 leaves, right? So we have uh, 393 leaves and one internal node can have a maximum of 256, right? And the minimum it can have is uh, seal of pi by 2, which is 128. Okay. So now we take two internal nodes. One points to, let's say, 256 leaves, and the other points to the remaining leaves. Okay. So we have two internal nodes, right? So we have these. This is the leaf level where the 393 leaves are there. We have leaf 1, leaf 2, leaf 3, leaf 4, and so on up to 393. We have two internal nodes. This points to, let's say, 256 of the leaves, and this points to the rest of the leaves. And we'll add one root node that points to this. So in B plus trees, the root nodes can have a minimum of two children, right? That is the only node with the exception that it can have two children. So we have created this B tree using maximum utilization, and the height of this B tree is 2, right? Height is 2. So the minimum possible height is 2. That's the answer. Okay. Let's look at the next question. Okay. We are given this schema that has 6 attributes, and we are given this functional dependency set. We have to calculate the number of super keys. Okay. So the first step in calculating the number of super keys is to find the set of candidate keys, right? So we'll do that first. We have A gives B, C gives D, and E gives F. Okay. So we want all those attributes whose closure will give you A, B, C, D, E, and F, right? So the first thing is to add all those attributes here that are not in the RHS of any functional dependency. So we have A, C, and E, right? Now let's try to calculate the closure. A plus A plus gives you A and B. C plus will give you C and D, and E plus will give you E and F, right? So clearly ACE is the candidate key, right? Now the super keys would be all the supersets of this from the given relation. So we have ACE, right? It would be AC itself would be one of the super keys. We can have ABCE, we can have ACDE, and so on, right? So we have ACE on one side, and we have three options, each of which can be or cannot be present. So we have 2 into 2 into 2, that is 2 power 3, which is 8, right? You can have 8 super keys because apart from AC, B can either be present or not be present. It has two options. Then D can either be present or not be present as a super key. So that gives us two options again. And F again the same. So it's 2 into 2 into 2, which is 8. Okay, fine. Okay, so let's look at this question, which is question number 55 from the sample paper. So we are given the following schema. We have two tables. One is the employee, and the second one is the customer. So in the employee, we have the employee ID as the primary key, and employee name and employee department. And the customer has the customer ID as the primary key with customer name, rep ID, and rating. Okay, so they're saying that the sales rep ID is a foreign key that refers to employee ID. Okay, so this is a foreign key that refers to employee ID. Now, they're saying that assume that each employee makes a sale to at least one customer, and we are given a query in which we have to find out what it will return. Fine. So we have select employee name from employee E where not exists, and then we are given an inner query that is select customer ID from customer C where C dot sales rep ID equals E dot EMP ID and C dot rating is not equal to good. So let's look at the inner query first and try to find out what it's doing. Right. So this is a correlated query for every tuple in employee E. This particular inner query will be evaluated. So let's see what it's doing. We have we want to select the customer ID from the customer table such that uh, the sales rep ID matches the employee ID and the rating is not good. So what we'll do is we'll have the customer table. Okay, we have customer ID, customer name, sales rep ID, and rating. Okay, so let's say customer ID one, name A, sales rep ID one, rating bad. Customer ID two, name B, sales rep ID one, good. Customer ID three, its name is C, sales rep is two, and it's good. Right. So now when we are looping through the employee table, for employee one, we are seeing we are saying select customer ID from the customer table where C dot sales rep ID matches the employee ID. That is, these two tuples will be put under observation, and the rating is not good. So for this, the rating is good. For this, the rating is not good. So the output of the inner query will be this tuple, right? Okay. And once the inner query is evaluated, we are saying that not exists. So which means since one tuple is returned, not exists would return false. And employee name of employee ID one will not be displayed. Right. Similarly, when we go to employee two, we'll come up with this, right? And since the rating is good, so the customer ID won't be selected, and an empty relation will be returned by the inner query. Then not exists will evaluate to true, and again the employee name for the employee ID 2 will be displayed. right? So based on this, let's look at the options. Option A says that the query displays the names of all the employees with at least one of their customers having a good rating. This is clearly false, right? We saw the example. One customer had the good rating, but still it was not displayed for employee ID 1. If you look at option B, it says that names of all the employees with at most one of their customers having a good rating. Again, that is also not true because this is the counter example, right? Uh, mm, Option C says the names of all employees with none of their customers having a good rating. Okay. So if that was the case, then employee ID 2 would have failed here because all of their customers have good rating, right? So option D says the names of all the employees with all the customers having a good rating. So this is the only option that makes sense based on the example. So let's try to logically reason it out, right? So now when will the inner query or when will the where clause evaluate to true? The where clause evaluates to true when the inner query will return no tuples. And when will the inner query return no tuples? The inner query will return no tuples when there is no customer uh, that is related to the employee who has a uh, rating that is not good, right? So basically, all those customer IDs for whom the rating is not good will be returned. And if there are no such tuples, that means all the customers have a good rating. Only then will the where clause evaluate to true. And the employee name will be displayed, right? So option D is the right option. It will display the name of all the employees with uh, their customers having a good rating. Okay. So I think those are the only questions we have. Yeah. Okay. So we have these many questions in the sample. I'll stop the recording. Okay. Okay. I guess we'll stop here. Yeah. Thank you.